Okay, this is part 2 of Unit 3C, and we're dealing with question 7, and that has to do with the absolute and relative errors. So to find that, you have the measured value minus the true value, and that gives you the absolute errors, and if you divide that by the true value and times 100%, you get the relative error. So, for this problem, we are given that the measured value is 12 feet 5 inches, and the true value is 12 feet. And so if we find this difference, we get a absolute error of 5 inches. Now to find the relative error, we'll take that difference, 5 inches, and we'll divide it by 12 feet. But we have to have like units, so we'll convert by dimensional analysis feet to inches. Now the feet divide out, the inches divide out, so our units are gone, and we'll also multiply by 100%, and that will equal, when the smoke clears, well, let's keep going with it, 5 over 144 times 100%, which equals 3.5%. So we had a absolute error of 5 inches and a relative error of 3.5%. Now let's go on to question 8. And question 8 has to do with accuracy and precision, and they're not the same. So let's deal with this. For 8, your true height is 70.4 inches. A tape measure that can be read to the nearest tenth of an inch gives your height at 70.5 inches. So there's a tenth of an inch difference. A second tape measure, which can be read to the nearest eighth of an inch, gives your height at 70 3/8 inches. So here's the height. The true value is 70.4 inches. One tape measure gives you a measurement of 70 3/8. That's 70.375. And another measurement is at 70.5, and these are all in inches. And notice the difference between these two is 0.1 inch, whereas the difference, I beg your pardon, did I? Yeah, a tenth of an inch, whereas the difference between these two is 0.025 inches. Now let's deal with the question. Which of these two measurements is more precise and which is more accurate? Well, the tenth of an inch is more precise because a tenth of an inch is less than, finer than, an eighth of an inch. On the other hand, the measurement that's more accurate is the 70 3/8 inches, because the difference between the true value and the real value, the absolute difference, is 25 thousandths of an inch. So B is our choice. Now for 9. And by the way, that relative to precision and accuracy, that information can be found on page 168. Now for 9, and this information for 9, which has to do with rounding, can be found on page 162. And so we've got to round appropriately relative to the number of significant digits. So at the beginning of 2000, the population of your city was 291,000. Now in significant digits, this has 3. The first 2 are accurate or exact. The third digit, the final digit, is always an estimation. Now, over the course of a year, your population has grown by 3,059 people. So 3,059. And so this is has 4 significant digits. The first 3 are exact. The third is an estimate. Now when we add these up, we're going to add an estimate to an unknown, and, well, we'll write this number down as we go. And 5 and 0 is 0, and 3 and 1 is 4, and 294. So now let's do the rounding. And when we add an estimate to an unknown, we get an unknown. So we'll put a 0 there. When we add 5 to an unknown, a known to an unknown, we get another unknown. So we'll replace that with 0. When we add a couple of unknown 0 to an unknown, we still do not know. Now when we add a known to an estimate of 1, we'll get an estimate of 4 when the other 2 values are exact. And there's our answer. And that corresponds to C, 294. Now let's do number 10. And for 10, we have to find the absolute and relative errors. And you can see this information on page 165. So we'll find the length of a piece of fabric is 27 inches, but you measure it as 25.6 inches. So we're going to take the measured value minus the true value. And by the way, the difference of those two is the absolute error. And if you divide by the true value and times 100%, then you get the relative error. So I'll just call it equals the relative error. So our measured value is 25.6 inches. And from that, we're going to subtract the true value, which is 27 inches. And the difference in these two will be a negative 1.4 inches, which equals a negative 1.4. And I'll put the units in here. And so that's the absolute difference. To find the relative difference, we'll take this difference, negative 1.4, divided by 27, multiplied by 100%, and that'll give us a relative difference of negative 5.2%. And there's our two differences. Now let's move on to 11. And so for 11, Determine whether the source of the error represents a random or systematic error, and counts the number of cars passing an intersection in a 15-minute period. Sometimes she makes an error in counting. Well, that's clearly a random error. It's not something that she would repeat. And so that's B. And by the way, page 163 if you want to review that. Finally, number 12. We have this value. In fact, let me write that down. So this is 12, and we've got a value of 8 point, and I've got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and finally a 1. Minutes. And the question is, state the number of significant digits and the implied precision of the given number. Well, the number of significant digits is 1, 2, 3, 4, 5, 6, 7, 8. Oh, I left out a 1. 9. So we have 9 significant digits. 9 significant digits. And by the way, I notice the answers provided are not appropriate for this question. They are incorrect. And finally, we have to have the implied precision. Well, the implied precision, excuse me, is to the nearest, let's see, we'll put a 0, and I need 6 zeros, 7 zeros, and a 1. 1, 2, 3, 4, 1, 2, 3, and a 1. And our implied precision is to the point 0, 0, 0, 0, 0, 0, 0, 1, and we are done. And that's a minute, so minutes. Good.